Today we will learn source transformation and the application of source transformation for reducing network. Here we can see a figure of a network where there are 4 voltage sources and 4 resistances. Now the question is, reduce the network shown in figure to a single voltage source with a series resistance. So how to do it? For that we have to learn source transformations. If say this voltage is VTH and this is RTH, like Thevenin's equivalent circuits, and this can be transformed to a equivalent current source, where this current source is equal to, the magnitude will be VTH by RTH, that is the short circuit current, and a parallel resistance. So any Norton circuit, from any Norton circuit we can get Thevenin circuits or Thevenin circuit to Norton circuit. That is, the voltage source with a series resistance can be transformed to equivalent current source with a parallel resistance. Now, in this problem, we can see objective is reduce the network shown in figure to a single voltage source with a series resistance. Ultimately, from this network, we have to reduce this network to a single voltage source and a series resistance. So we have to find out this voltage source and this resistance. So how to do it? So as I told you, a voltage source and a series resistance can be transformed to an equivalent current source. Another concept is required to understand. So we can add the voltage source when they are in series. This is V1, this is V2, is equal to, equivalent voltage source as V1 plus V2. Another concept is current source. We can add the current source when they are connected parallel. So this is I1, this is I2. I can write as single current source I is equal to I1 plus I2. Now, if the current source is one is in reverse directions, this current source in this directions and this current source is in these directions. So whatever may be the value of I1, I2, which one is greater? So ultimately say I1 is, if I1 is greater than I2, then the equivalent current source will be like this, I1 minus I2. If I2 is greater than I1, that time this will be downwards. That time it will be maximum. So it will be I2 minus I1. Okay. So based on these principles, we have to reduce this network. Remember that an ideal voltage source is one which gives a constant voltage V irrespective of the current drawn from it, that is the source impedance or resistance is 0. And any physical source is represented by a resistance in series with an ideal voltage source. An ideal current source is one which keeps a constant current irrespective of the voltage across it. That is, the source impedance or resistance is infinite. Hence, if it is required to convert a voltage source V in series with an internal resistance R to an equivalent current source, it is done by replacing the voltage source with a current source of value V by R. So here we can see 8 volt, 2 ohms. So we can convert it to equivalent current source. So how? This is V is equal to IR. So I am transforming into current source. So 8 volt by 2 ohms. So it will be 4 ampere current source and a parallel resistance 2 ohms. Okay. Now another 6 volt 1 ohms. So what I am doing, this is, it will be again V is equal to IR. So this I will be, what will be the value of current? Tell me.
6 ampere.
Right, 6 ampere. And the resistance, this is parallel to it, is 1 ohms. Now we can see at the top, there is 3 volt 1 ohms in series. And this is 6 volt 2 ohms. So again, I am converting it to equivalent current source. So it will be 3 ampere. And 1 ohm will be parallel to it. And this is 6 volt 2 ohm. So if I convert it to equivalent current source, so again it will be
3 ampere.
3 ampere. And this is 2 ohms. Now the next diagram will be, we can say this is 6 ampere, 4 ampere. So in the upward directions, so it will be 10 ampere. The equivalent resistance is 2 ohms parallel 1 ohms. So 2 parallel 1 is equal to 2 into 1 by 2 plus 3. So 2 by 3 ohm. Now this is 3 ampere. This is 3 ampere. Again, this will be 6 ampere. And again, 2 and 1 ohms are in parallel. So this will be again 2 by 3. Now this is the situations. Now I'm converting this to equivalent voltage source. So V is equal to IR.
Ma'am?
Yes.
Ma'am? Ma'am, could you repeat how you simplified the circuit in the last step?
Lobster, sure. Sure. Can you see this is 4 ampere and 6 ampere, both are in the
Yes, I
upward
can see.
directions.
Hmm.
So I told you that when the current in the same directions, we can add it.
Oh, acha.
Okay, the same direction, so I am adding it one. So this is 10 ampere. And this is 3 ampere, this is 3 ampere. Again, they are in the same direction. So again, this one is the 6 amperes. And resistance are connected parallel. So I have written the equivalent value of the resistance. This is 2 by 3, this is 2 by 3. Okay?
Okay, ma'am. Thank you. Got it.
Next, so this voltage will be V is equal to IR. So this value will be 10 into 2 by 3. So 20 by 3 volts, right? And resistance, this will be 2 by 3 ohms. So this will be again 6 into 2 by 3. So this will be 4 volt. And the value of the resistance is 2 by 3. Now I told you that 2 voltage source, we can add it, they're in series. So that time, the value of the voltage source will be?
4 by 3, ma'am.
Yes. 4 by 3, not? This is 20 by 3.
32 by 3. Oh, mistake, ma'am.
20 by 3 plus 4 volt.
32 by 3.
Yes, this is 32 by 3 volt. And the value of the resistance is 2 by 3 plus 2 by 3. 2 by 3 plus 2 by 3. This is 4 by 3 ohms. Clear? So from this figure, we can see there was 4 voltage sources and 4 resistances. Now, the question was reduce the network shown in figure to a single voltage source with a series resistance. So in this figure, we can see a single voltage source and a series resistance. Okay? Clear?
Yes, ma'am.
Okay.